Okay, so we're going to write integrals as a limit of Riemann sums. Okay, that's what we're starting with right now. So in this case, we have, there we go, that's good enough. Okay, the integral of cosine x dx from pi to 2 pi. So the first thing we have to do is we have to determine our delta x. Now, I say first, but there's no first. But this is what we do. And all we do is take our top boundary, we subtract our bottom boundary, and we divide it by n. Okay, that is our delta x. All right, so that's the first thing we do. We're really talking about this piece right here. Okay, all right. Next, we need to find our x sub I term, or we sometimes see it as our kth term. So it's different. X sub I, x sub k are the same thing. So kth term or ith term. In this case, it's going to be pi plus our delta x, which is pi over n, times I. So our pi comes from here. So we have our starting value plus our delta x, which is pi sub n times I. And this is our ith term, and this is for a right-hand rectangular. If it's a left-hand rectangular, then it would not start with pi. It would simply start with that first one. But we don't do rectangle. We always do right-hand. All right. Then I'm going to rewrite this whole thing, and I'm always going to write this first part the same way, which is limit, okay, as n approaches infinity. You're going to always have our sigma there. Pi equals 1 to n. All right. So this is always going to be the same every single time. And then we're going to have our function, in this case cosine. And then we're going to have our ith subterm, which is this thing right here. Pi plus pi over n times I. Close that. All times delta x. And that is our term. I'm looking for a nice blue color. There we are. That is our solution. And that blue and pink really pop. All right? So this is our original integral. We take our delta x. We find we take our boundaries, or 2 pi and pi. We find our delta x, which is pi over n. Okay, 2 pi minus pi divided by n. We then find our ith term by taking our lower bound, in this case pi, and adding our delta x times I. Let's get our ith term. And then we rewrite the whole function. This limit part is always going to be the same. As n goes to infinity, I equals 1 to n, cosine of the xi term, and then times delta x. Now, I say this is always going to be the same. If we're writing this out, that's the way we want to write it. Right? We can talk about our delta x approaching 0. Like we talked about this before. We could have our delta x approaching 0. That would be the same thing as number of rectangles approaching infinity. Okay? All right. And if we're talking left hand, we're talking I equals 0. But don't worry about that. I don't even know why I said it, because all we have to worry about is the right hand side. Okay, next one. Okay, so 0 to 3 of e to the x dx. All right. So our first step is to find our delta x, which is 3 minus 0 divided by n. So our delta x is 3 over n. Okay. Our next step is to find our x sub I term, and it's our starting value, in this case 0, plus our delta x, 3 over n times I. All right, which is obviously just 3 over n times I, or 3i over n, either one. And now we rewrite it, and we do limit as n goes to infinity of our integral. It's a horrible integral. I equals 1 to n. Our function, in this case e, raised to our ith term, raised to 3i over n, or equivalent 3 over ni, 3 over n times I, times delta x, times 3n, 3 over n. And that is our integral rewritten as a limit of a Riemann sum. All right, a couple more practice ones. This next one I'll let you do yourself. Okay, let's do this yourself. All right, so there's your function. Okay, pause the video, go ahead and do it. Okay, great. Now we're back. So, we do our delta x, which is going to be equal to e minus 1 over n. So there's our delta x. We do our ith term. All right, it's our starting value, 1, plus our delta x, all times I. Okay, so this is, we're talking about starting at a particular value and moving over that much, that I. So if we moved over 2 i's, if I was 2, we'd move over 2 of these. If I was 3, we'd move over 3 of these. So we're starting here. This is just the length of our rectangle, or width of our rectangle, and we're evaluating the function at that value. So I then rewrite it. Limit as n approaches infinity of 1 equals I to n, and then this, we put our function back in. ln of our ith term, 1 plus e minus 1 all over n times I, all times our delta x. And that is our limit Riemann sum of that integral. Okay, do this one yourselves. I'll give you 15 seconds or whatever. And then we'll go. All right then. Now, our delta x is 7 minus 3 over n, or 4 over n. Okay? Our x sub I term is equal to our starting value of 3 plus our delta x, so 4 over n times I. Okay, once again, let me say this again. We're starting at 3, and if I is 1, if we're on our first term, then we're adding 4 over n. That's our delta x. And then, n being the number of rectangles. And then if I becomes 2, then we're adding 2 4 over n's, or 3 4 over n's. If I is 3, so on and so forth. So this is simply starting here and moving down the line that many i's. Okay, then I'm going to rewrite this entire function. Limit as n goes to infinity. Horrible infinity symbol of the summation. I equals 1 or 1 equals I. Either way is fine. To the n, and then my function is 4x cubed, but remember our x is this. There's my x, okay, that's my xi term. This is all cubed, and then this is all times delta x. Okay, there's no need to go further here. You don't need to simplify this, multiply the 4 by 14 or anything else. That's perfectly fine. Good. All right. I'm not sure why I wrote that so closely. All right. Okay, now we're going to go the other way. Okay? So now we're going to go from the Riemann sum to the function. All right? We're still going to start with looking at this piece right here. Okay? What that means is my integral has a span of 5. Okay? From 1 to 6 or 9 to 14 or something, but there's a span of 5. Okay? And then we look inside here and we have this as our starting value. So as you recognize, this is the same as always. So if this is our starting value, that means my integral has a 2 on the bottom. Right? It's a horrible integral. Okay? So my integral has a 2 on the bottom, and I know it has a span of 5, therefore I know it has a, 7 on top. So 2 to 7, or 2, that's a 7. Okay? So because this is a span of 5, because the 5 there, we have that span there. We know our function is ln, or natural log. Now we have to look into here. This is the starting value, so I'm good there. Let's check. I'm adding delta x. So really, this is just simply exactly what this is, 5 over n times I. So this, I don't have anything to do. This is simply my first xi. This is my xi term, and I am done. All right? It looks a lot more daunting than it is, but let's take a look at it again. Our delta x, this 5, tells us how far this distance is. This 2 tells us this number, which means this has got to be 7. Okay? My function here is ln. It's ln. And the question is, what is that stuff? And that is the starting value, which is 2 already, so we're good there, plus our delta x, 5n times I, so we're good. So this is a basic old x function. And that's that. All right? All right, let's do a different one. Okay, forget this. Okay, take a look at this right here and pause it and see if you can rewrite this as an integral. Okay, good. Unpause. All right, so we're talking about, we have an integral, obviously. Our bottom number, well, delta x is going to be 4 over n, so this, we know this distance between these two numbers, from the bottom bound to the top bound is going to be 4, and we know our starting value is 3. Therefore, we know our top value is 7. Okay? We then know that our function is this number 3, which is our starting value anyway, so we're good, plus delta x, which is 4 over n times I. This is simply my xi term. So I'm good. So this function is x squared dx. Don't forget the dx. And that's your solution. Okay? So we have our delta x of 4 over n always. We have our starting value 3, so we're good there, 3 or whatever. This becomes 7, and then this is simply xi squared. So even though we're not going to be dealing with multiple choice problems tomorrow, let's take a look at a multiple choice problem and sort of see where we have to go or not go. Okay, so we have our range. This is b minus a, right there. So we know 5 minus 0, that works. Okay, 4 minus 0, that's a no. 9 minus 4, that works. 9 minus 4, that works. Okay. We have our starting value of 4, which means we have to have a 4 down here. So that's a no. That doesn't work. So now we're down to 2. All right, we're down to these two problems right here. And then this becomes, well, there's a lot of stuff going on in there. 4 plus 5i over n times 5 over n. So really, this feels right, okay? But this is not, I'm not plugging in a 4 here, or this is not part of my function. This whole thing is my x sub I. This whole thing is, okay, what's my very first value I'm going to evaluate at, and it's 4, plus 5i over n, and then this is my right-hand estimate for my rectangle, remember? So that's just this whole thing is my x sub I. So even though this 4 looks like it should be there, it shouldn't. It's simply 4 to the integral of 4 to 9 and the square root of x. And that's that. All right. So that's it, folks. That's the integral problem. All right. Talk to you tomorrow.